Okay, so hi everybody. Today I will present asymptotic analysis of games with many players and weak interaction between the players, dealing with equilibrium, optimal costs, where the main result is fluctuation, which is the central limit theorem in a functional sense. Okay, so the content is going to be as follows. First, I'm going to introduce a finite state many player game with weak interaction between the players. And I will present the master equation. The master equation is some sort of equivalent to the AJB equation that we have or in the N player game. But the master equation is the AJB associated with the mean field game. Okay, so in order to obtain the fluctuations, I need preliminary approximation result where the empirical measure of the players is coupled with some sort of auxiliary empirical measure, which has a simpler form. And while the empirical measure under the equilibrium of the N player game depends on the solution of the AJB associated with the N-player game. Here, in the second part, I will construct empirical distribution that is associated with, instead of the AJB, it would be the master equation. Okay, and it has a simpler form. And those two measures are shown to be close to each other by order of 1 over n. And then you can understand now that if the difference between them is of order 1 over n, applying the central limit theorem for one of them, which deals with the square root n, 1 over square root n, it would imply also to the other. This is why we are working with something which is simpler, but would have the same rate of convergence. Then I will present the fluctuations and eventually the fluctuation results. And eventually the conclusion and future outlook and some other models that were being studied quite recently. Okay, so first of all, let's deal with the N-player games. Okay, so some literature, many player games, N-player games, when N goes to infinity, is associated now with mean field game theory. And mean field game theory is devoted to asymptotic analysis of such games where you have many players, but they are weakly interacting. What do we mean by weakly interacting? It means that each player affects on the others very weakly. And in what sense weakly? In the sense that one player almost does not affect the behavior or does not affect the dynamics of the other player much. For example, if we all invest in the market and I go and I buy today one stock of Amazon or not, it will not affect other investors so much. It will not affect the market so much, right? Because I'm a small player. And when we have many small players, this is one type of mean field games. There are also types of mean field games where you have major players that have more effect on the other players. Okay, so mean field games initiated on 2006 in the work of Lazary and Lyons, and also at the same time by Wang, Keynes, and Malame in these 5 papers that I give here. I'm not going to give the entire history of mean field games. We have 15 years of papers behind us. I want to mention one paper, which is by Gomez, Moore, and Sosa. This is about continuous time. And the emphasis here is going to be on finite state mean field games. It means that while the previous paper I listed in 1 to 5, they deal with diffusion processes that players are controlling. In this case, in paper number 6, each player controls a Markov chain. Okay, so a finite state Markov chain. So this is a big difference between the two models, mainly technically. Okay, I just want to mention that there was another paper that studies finite state mean field games with more or less same results, and it was uploaded to arXiv on the same weekend that we uploaded our paper, and it was submitted to another journal. Both of them were published. And at the end, I will give the papers on which my talk focuses. Okay, so some more literature. So there is mean field games. Mean field games, there is a vast literature on it. Now there is another concept in mean field games, which is the master equation. And you can see that the master equation initiated quite recently, which was on 2014. I don't want to say which paper came first and which not. All of these papers are important, but sorry, let me grab my pen. But I think the main paper that made the most buzz was paper number 6, which was a paper, but then it was transformed into a book by Cardelier, Delarue, Lazarine, Lyons, and they used a master equation to show convergence of n-player games to the mean field game. Okay, so this, the work I'm presenting here is more or less is influenced by this work and gave similar results in the case of finite state mean field games, and it goes one step beyond this to give the central limit theorem. And the central limit theorem was also given by Delarue, Lacker, and Kavita Ramanan in the paper. I cannot write. In the paper that we have here, number 7. And they also studied the law of large numbers. I'm sorry, the large deviation in another paper. Okay, and there is another list of papers. I'm not going to go over them, but if someone wants this literature, he can contact me, or she can contact me, and then I can give the presentation. And this talk is based on the paper Analysis of a Finite State Many Player Game using its master equation, which was published on Cycle. Okay, so let's go to the model. And in the model, we have X states. Okay, I'm going to use the letter X only one time in the future. We have n players, and the horizon is finite with capital T. So to make this talk to use illustration, let's assume that we have a playground, and we have many kids in this playground, and for simplicity, 3 states, and each kid in this playground chooses the rate to move from one state to the other. And by choosing the rate, we can see that there is a stochastic dynamics of the players within this 3-state Markov chain. And why do I call it Markov chain? So xi is going to be the private state of each player. Okay, for player number I, xi is going to be the private state of this player. Mu minus I is going to be the empirical distribution of the other players from player number I's point of view. So this would be the empirical distribution. And A of the ith player would be the rate to move when the time is S and the private state is X. The empirical distribution of the other players is mu minus I. So the rate to move from this state X to the state Z is denoted by this long A. And what is the private cost? Each player has a private cost, which is J of, we indicated by N and I to indicate the player. So this is time, we have the time, we have private state, we have empirical distribution of the others, and we have control. So all of these terms, they come into effect where we have X is the dynamics of player number I, where player number I starts at time 0 at state X. The empirical distribution of the other players starts at time t, at time little t at eta. This is the control that each player uses, and this is a terminal cost. And the goal of each of these players is to bring this to minimum. Okay? Our goal in this work is to find the fluctuations for the empirical measure mu n, I did not define what is mu n. Mu n is like this, like what we have here, but only that we divide by all the players and we take sum over all the players. So this is mu n. Okay, so this is the structure of the model. Okay, so as you can see, as you can see, the interaction between the players comes through the empirical distribution. So each player is affected by the other players because my cost depends also on the positions of the other players in this game. So if one player moves, I will not be affected so much. Okay, and if I move, the empirical distribution of the others will not be affected so much. The one point that I want to, another point that I want to emphasize is that in this game, the control is Markovian. It depends on current state of the entire system, and it depends on S, on the time S. It does not, it is not we call this a closed loop controls versus open loop controls, which were studied at the beginning of the theory of mean field games. Okay, so the AJB equation. How do we analyze n-player games, and what is the relationship to the master equation? So I hope that this talk, at least the next couple of slides, will give you an idea what is the master equation. And since I'm starting from a model that I guess all of you can understand because it consists of finite state mean field games, while in the diffusion case, in order to define derivatives with respect to measure, we have to do some lifting and to define Lyon's derivatives, which are a little bit more complicated. Here, everything is very, very tractable. Okay, so let's fix a strategy profile beta minus I for the other players. Okay, this is the other players. And a strategy AI for myself. I'm player number I. So I'm assuming that all the players are playing beta minus I. Eventually, what we will want to do is to find symmetric Nash equilibrium. I would like to equate this beta and AI to make sure that all players are playing the same control. Okay, so if I take the value function, and this would be the value function that depends on the other player's beta, then of course it is less or equal, okay, if I play AI, okay, because AI is some control that I'm playing. It is still not the optimal control. But given that the other players, and I will emphasize here, the other players are playing beta, my optimal control, I don't know it. Let's try to characterize it. So I'm just using J as my cost. Okay, I'm just plugging in this from before. And we have, this is terminal. This is the terminal cost. So I'm just plugging in Vn at time capital T. Okay, this is standard. And now I'm using Ito. Okay, so now we'll explain each of the terms that we have for this equation. So let's see. First of all, the blue part, this part, the integral, I just copy paste it here. So there is nothing to understand over here. The Ito I applied is only for the function V, capital V. Okay, so V at time capital T is V at time little t plus all the integral that we have here. So what is this integral consist of? So we have, first of all, I'm taking partial derivative with respect to time. Okay, I'm saying Ito, but this is because in the diffusion we'll call it Ito. This is just finite state Markov chain. These are regular integrals. So this should not be something that is complicated. So first of all, derivative with respect to t. And now we would like to take derivative with respect to the state. This is what often we do. But instead of taking derivatives, we're saying, oh, the process xi, my process, can change from xi to z. As you can see, this stays the same, this stays the same. So I'm just changing the x. So x changes from xi to z in this rate. This would be the rate that I am moving from my own state to state number z. Okay. What is the next? So if it was just regular Markov chain that I'm controlling my own Markov chain, there are no other players, this is where we would end. Okay, just this part. But there are also the other players. So what is this? This is the number of players in state Y, because the empirical distribution times n-1 is number of players. Now, each one of these players moves with rate beta from state number Y to state number Z. This is the rate to move from Y to Z. And as you can see, if one player from state number Y moves to Z, then what I'm doing, I'm subtracting EY, where EY is 0, 0, 1, 0, where this is the Yth position, Yth place. So I'm subtracting one player from there, and I'm adding one player for them from to Z. And therefore we have 1 over n-1, and this is the change in U minus I. Okay. So all over the talk, EY and EZ would be just the standard basis vectors. So now I'm looking at this and I'm saying, oh, if I'm erasing on both sides this Vn, what I'm getting is that everything inside should be greater or equal to 0. And under optimality, it should be equal to 0. Okay. So this is what I have here. I can construct from this, I can construct the AJB equation. Now I put this rectilinear shape because my control only enters in these two places. This is the other players, the last line. The other players are not controlling, they're just using their beta. So if I'm looking for an AJB or to find an optimal solution, I will just look at this shape. So I just rewrote it 0 equals partial derivative with respect to t. This is what I have here. Now I created the blue part is anything inside this rectilinear shape plus what we have at the bottom line. But the only thing I did, the only big change I did is that I don't have any more processes here, right? No processes. I just plugged in all the states. All the states. Okay. So now I just want to have another notation which will make things a little bit simpler the way I'm writing them. So instead, what we have over here is delta xv. I write delta xv where I have the x over here. It is just a vector of vn z minus vnx, where I'm keeping the x fixed for all the vectors. I'm subtracting vx from all the vz's, and I'm multiplying by a. Usually, if we would have diffusion, what we will have here, this part is going to be the derivative or the gradient of v times the vector a. Okay? Okay. So now, I'm just plugging this here. Okay, I'm plugging in the optimal A star. And now what we expect that in symmetric equilibrium, we will take beta minus I to be A star. Okay, I want that the other players and me will play the same. This is when we will have equilibrium. So far we just had a regular type of AJB, but the nice thing that we have here is that we are comparing between me and the other players. So now I'm replacing this with A star for the other players. And the order of 1 over n that I have here is because now this is the A star is a decision from the other player's point of view. Okay, this is not me doing this A star. I was choosing this A star, but this was the beta. The beta was another player. Okay, so the other player, she sees another empirical distribution. She sees the empirical distribution from her position. Seeing this from her position, she, for example, sees me and she does not see herself, while I see her and I do not see myself. So there is a small difference of order of 1 over n that is negligible in the limit, and therefore I do not insist on it right now. Okay, so now we're trying to take the limit of this strange AJB equation, or I would say AJB with a fixed point. So if we're looking at this term that we have here, n minus 1 times, we have difference between these two v's, okay? And we have plus EZ minus EY, and we have 1 over n minus 1 times n minus 1. So one can show that at least in a formal way or informal way, which is the same, this can be approximated more or less by this in case V is differentiable. Okay, I'm not getting into this because I'm just giving an illustration how to set up a PDE that is associated with the mean field game, or what we call the master equation. Also, we will use the fact that, you know, in Markov chains, the rate to move from one state to itself is actually 0. But for technical reasons, in the rate matrix, we are denoting this by negative of the sum of all the other rates. So using these two observations, what we get is that partial derivative of Vn, I would approximate it by partial derivative of u. The blue part, this is just the Hamiltonian. It will just be this blue part that we have over here. And now, thanks to the fact that we have this A star, the special A star here, the rate is just a negative. I can write, and this box here, I can write the rest of it as n eta y, partial derivative with respect to eta z, running over all the y and the z, and times this rate. So this is what we call the master equation. So the master equation is actually just the AJB with the fixed point in the limit. Okay, so the master equation is associated with the mean field game. The mean field game would be more or less the same game, only that we don't have n players. We are playing against mass of players, or against a measure of players that evolves in time. So, of course, the natural question is, what can we do with the master equation? What's the point of this equation? Yes, so I can characterize, let's say I can characterize the mean field game with the master equation. What else? What else can I do? How can this help me saying anything about the n-player games? So this is part of the talk today, part of the goals of the talk today. So some assumptions that we have in this model. The first assumption, control set. Okay, I'm assuming that this is compact set bounded away from 0. Okay, one may relax this assumption that it is bounded away from 0, but we still need some compactness. If there is no compactness of the control set, one can artificially generate it, as often done in games, where you would have the function. For example, if the cost function is quadratic in A and your control is linear in A, then of course you would not like to choose big A because your penalty is quadratic while your control is just affected linearly. So this is a way, for example, to generate artificially a compact control set. So this is not a big deal. Okay, separation. Separation, this is a classical assumption in mean field games, where you separate your control from the empirical distribution. So eta stands for the empirical distribution. A is my personal control. So we separate them into two functions. So we'll soon see where it comes into effect. Lipschitz. Okay, Lipschitz continuity. So now we need stronger regularity assumptions, and the stronger regularity assumptions are for the terminal cost G, and for the function f2. I need it to be Lipschitz in eta, but also that the gradient would be Lipschitz in eta. Okay, so this is a little bit strong. And the monotonicity assumption. The monotonicity assumption, which is summarized by these two, one for G and one for F2, so the first one to suggest it was Lazare and Lyons. This is why it is also often called Lazare-Lyons monotonicity condition. In this case, the players would like to avoid congestion. Okay, players would not like to be next to each other. This is like a very classical social distancing type of condition. And the advantage of it, and I would say maybe the only reason we have it, is because it guarantees uniqueness. So far in mean-field games, this is like the most fundamental assumption that we have that guarantees uniqueness. Towards the end of the talk, I will say a couple of words what happens if we don't have such such condition. And concavity on compact sets. This is for H1 in pink, but I did not define what is H1, this magenta H1. So now I'm defining it. So since our function f can be separated, the eta and the a, into two parts, so you can see that inside the Hamiltonian, which I now call H1 in this pink, so this is compact, okay? I'm sorry, this is a concave function, the H1, which, for example, would work if f is convex in A, sufficiently convex. The nice thing that I separate the eta from the A is now that at each time, whenever I want to optimize my A, I do not do this. I do it regardless of the other player's position. But this is not accurate. Remember that here we should plug in the value function. Usually I would plug the derivative of the value function. Now I'm plugging in the delta of the value function. And the delta of the value function depends on the other players. So this is a little bit tricky. I do depend on the other players, but only through Vn, okay? Not directly. I mean that my control does not directly depend on the other players, only through the Vn. Okay. So the assumptions in most part of the paper are less restrictive, and A star can directly depend on eta. Okay, so in my paper, I do allow for F2 eta to be inside here, but then I need the assumptions that we have here that I will have in the paper instead of these ones will have an uglier structure. So I preferred here to give a little bit more restrictive assumptions just to give the big picture. Okay, so regularity of the solution of the master equation. So now the assumptions that we have imply regularity of the control. Moreover, so now using PDE techniques where we'll linearize a coupled of forward-backward system, you can imagine that you have forward for the measure goes forward. We start with some measure of the players, but then they play and there is a measure going forward. And backwards, this is the value function that always goes backward. I wrote it here, measure and the value function go forward and backward. And we were able to show not only that U is Lipschitz, but also that the gradient is Lipschitz. Remember that in the master, we have the gradient of U, and we want this term to be Lipschitz. Okay, so this is why we also needed the assumptions. Sorry, let me go back. The assumptions that we have Lipschitz continuity of the gradients of f and g, because we would like to inherit this property for the function u, which will solve the master equation. Okay, so now let's have a couple of minutes on the approximating of the value function. So I give here again the master equation. I repeat the question, what can we do with the master equation? So now proposition 1 that we have in our paper says this: supremum over time of what is Vn minus u. Vn is the value function in the n-player game for each player. U is the solution of the master equation that exists and it's sufficiently smooth. And now I'm taking the equilibrium path. I'm saying, okay, there exists an equilibrium. Okay, this is the existence of equilibrium in the n-player game. This is not, I'm not going to go over it. This is a result that is already known. I will soon state where it's from. So the difference between the two under the equilibrium path, plus I can also take the delta between the two functions. In a diffusion case, this would be the derivative. Since we have the square here, we have square here. But in general, it just means that the difference between Vn and U is of order 1 over n. To prove it, we're using Ito's lemma, Gromov inequality, the structure of the AJB and the master equation. So it's not that enlightening to show it in a presentation. I want to emphasize that in the beginning of the talk, I gave a paper. I listed a paper, Gomez, Moore, and Sosa, continuous time finite state mean-field games. And their results, they show convergence, but only on a small time interval because they are going through the forward-backward system. And convergence of forward-backward system, if you don't have enough regularity, it holds only on sufficiently small interval. Because over there, you would need to do Banach's fixed point theorem, you need a contraction mapping, and for this, you need the time horizon to be small. But when you use the master equation, the AJB and the master equation, then under the same assumptions that Gomez, Moore, and Sosa had, maybe just a tiny bit stricter, you would get convergence on any time interval. So this is already an improvement. Okay, so now the second part is approximating the empirical distribution, and for this we're using coupling. Okay, so now we are considering two processes. One, the x's under the equilibrium, and the second set of processes are the y's. The y's are y1 to yn, and the transition rates of these processes, they do not depend on Vn. Usually previously we had Vn. The control was dependent on the delta of the Vn. But when you have control depending on the Vn and you have n players, n appear twice. The parameter n appears twice. It appears first in the number of players, and the second appearance is inside the Vn. What we are doing here is we're saying, okay, let's keep the n players, but instead of Vn, let's replace it with the u. When we replace it with the u, taking a limit would be much, much easier because you have only one n to take to infinity. You do not have to take care for the Vn. So now if we have these two processes and there is a coupling, okay, that's the second proposition. There is a coupling between the real equilibrium and the fake equilibrium such that the difference between the two measures again is of order 1 over n. So how this coupling is done? This is very, very easy. So suppose we have, for the blue part, this is the y players, the one who are using the master equation, and the red side, the x's, are using the Vn. They're using Vn. So suppose that the process, okay, we are constructing y and x together, so they would both jump. If the rates are like this, like the arrows that we have, alpha 1 and alpha 2, beta 1 and beta 2, they would both jump to the state 1, 1, both jump together to 1 with the minimal rate, with rate beta 1. So this is the first line that we have here. But there is also this alpha 1 minus beta 1. So this is just the blue player is going to jump here, and the red player stays at her own state. So this is this difference. I can do the same for the other side and get this alpha 2 and the difference between the two. The only observation I want us, I'm sorry, and the coupling of the player of both pairs is going to end at the first time they split. So once two players in this game split it, they didn't jump together, then we're finishing the coupling and we're saying, okay, now each each team just go on your own. Just the x's just move independently from the y. We're not coupling between you anymore. And the key observation here is that the splitting rate between them is alpha 1 minus beta 1 plus beta 2 minus alpha 2. It's just these two gaps that we have over here. This would be the rate that they split. And by the way, how much time do I have?
20 more minutes.
Okay, great, thank you. Okay, so how do we prove this theorem? We remember the theorem said that we need to show that they are close to each other by order of 1 over n. So the expectation of this supremum between them, first of all, I can bound it by 2 times. And now notice I'm taking expectation of the difference between the empirical measures, and I'm just comparing them to 2 representative players, xi and yi. And why this is true? This is very simple. Remember that ex is the vector of the standard basis. So when we have this minus this, so imagine that you have vector of 0, 1, 1, 1, only 1 in one place, and then you subtract maybe 1, 0, and the rest of them are zeros. So what you would have in absolute value, you would have the 2. This is why you have the 2 entering here. And x's, the x's that we have here are states. So it would be one of these numbers. So of course we're only enlarging when we go here to the right. This is why we have the first bound. Okay, so this is the difference between 2 players. Okay, so I can also bound this by, this is the probability that until time t they were splitted. Okay, tau and I, they were splitted before this time. Okay, and x minus 1, this is the number of states that we have minus 1. So the difference between x and y, right, the difference between them cannot be more than this gap, the gap that we have between the last state and the first state. So this is why we have x minus 1. This is the difference between them, and the probability that they split it before, because if they did not split, then they are the same. Now we're using the key observation. So because the rate is, we're talking about the Markov chain, this is where we have this exponential term that I wrote here. And this is just the splitting rate. What I write here is just the splitting rate. The splitting rate is exactly the difference between the 2 alphas. And now I can use a 1 minus e minus x less or equal to x, like to use one of these inequalities that we usually have. So I can just bring the sum that we have here on top, I'm just bringing it down to the same level, no exponent. And the assumption that we have from before, they would imply not only that U is Lipschitz, but also that alpha star is Lipschitz, the optimal one, or the equilibrium one. And therefore, we can just somehow from here, because we have that alpha is Lipschitz, okay, and we have the Vn and the U would enter here. Remember that the Vn and the U, the difference between them is of order 1 over n. And so we can use Grunwald's inequality, right? We have on the left-hand side here, we have the same thing that we have here, or we can enlarge it by putting supremum inside this integral, and Grunwald's inequality will give us exactly what we want. Okay, so this is the idea of this proof. So far, what we have is that the value function Vn and U are close to each other. The empirical distribution and the empirical distribution of both coupled systems are close to each other, both in order of 1 over n. And now it's time to get to the main result that we have in this paper. Okay, so the main result is let's set a matrix alpha xy, which is the rate to move from state number x to state number y, given the time t and eta. And notice that here I'm using the solution of the master equation. What is mu t? Mu t, this equation that we have here, this is the standard Kolmogorov equation that we have for Markov chain. This is the mu t is the distribution of the players in the n player game, or I'm sorry, in the limiting game. I did not define the limiting game, but when mu n goes to infinity, you can imagine that you have some sort of convergence to some measure. So this is the dynamics of this measure. The dynamics of this measure would satisfy this. Okay, this is just standard Kolmogorov equation. Imagine Markov chain, and you start from some distribution, then the evolution of this distribution according to rate matrix or rate function alpha would be like this, where this is the initial distribution. And let's assume, so this is not real assumption. I mean, if we want to prove a CLT result, we need to assume that at least at time 0 we have a CLT. Okay, so at least at time 0 we have some convergence. Then if we have at time 0 this convergence of order square root of n, then mu n, the empirical distribution of all the players, mu n is the empirical distribution of all the players, converges to mu, and it will not only converges to mu, if I multiply it by square root of n, I will get that there is some diffusion process that matches this psi t. If it was just a time at one time, then it would be like central limit theorem, it would be normal distribution. But we're talking about set of processes mu n that converging to mu, then we have a diffusion process. I wrote here intentionally function of mu and psi, and here I wrote sigma. In fact, we have a full characterization of all of them, but I don't want to give this full to focus on the full characterization here. So right now, let's ignore this. We will see it through the proof. We'll get this, this shape. But now I just want to focus on this structure that we have a drift and we have a diffusion coefficient. And what is the key idea? I mentioned it several times, that instead of working with the mu n, I can work with the nu n, the ones that are close to the mu n up to order of 1 over n. Okay, so now I want to prove the theorem, and this is what the next 5 minutes will be devoted to. Okay, so some notation. The notation is AXN at time t. This is the number of players that moved into state number X or arrived at state number X until time t. The rate of this, let's motivate this, is going to be n times lambda, where lambda is defined this way. So let's see what it's going to be. This is the number of players in state number Y. So now we have, if I multiply this by n, so this is number of players in state number Y. Players at Y. And each one of them moves to state number X in this rate, alpha YX. Okay, and I'm plugging in the empirical distribution. Remember, the order of 1 over n depends on the point of view. We don't care about this. Okay. Now, instead of arrival with the letter A, we're going to S. S is the number of players that moved from state X until time t. And here I'm using the letter S because they think about them as being served. Like they were in this state and then they were served by a server. I'm sorry. So now this is easier because we are talking about players who left state number X. So this is the number of players. And they moved to state number Y with this rate, alpha XY. So the nice point here is that while here we needed this to be inside, this is new X, this is not new Y, because this is the number of players that move state X to Y, to Z, to W, while before here, the number of players arriving, they could have been arrived from many places. So we care where they came from. This is why the new it was inside and now it's outside. Okay. So nu n, which is the empirical distribution, is just the initial distribution plus arrivals minus departure. Okay, so I'm dividing by 1 over n because the nu n is empirical distribution. So it is defined by 1 over n. I would also denote a tilde and s tilde as the scale, diffusion scale, because I subtract from a, I subtract the expectation and divide by square root of n. Same I'm doing with s. So over here, I just wrote what we have here on top. Okay, so nu and t is just the initial plus what we have over here. But because I subtracted here the expectation, subtracted the expectation, I need to compensate for it and cancel it and cancel any appearance. I mean, I added and subtracted, I just need to fix it. And here, I also give, this is the Kolmogorov equation that I mentioned earlier. So if I'm taking the same equation, this is just copy pasted from the last slide. So I'm calling the first limit the fluid limit. Usually in stochastic networks, this is how we call it, because this is the law of large numbers. Like in fluid, it just goes in rate of 1 over n. There is no diffusion. There's no noise in the limit. So to get this convergence, we have supremum. Okay, I'm just using the triangle inequality with all the terms that I have over here. I'm recalling that alpha is Lipschitz. Okay, so since alpha is Lipschitz and bounded, so we have nu n and mu. We have alpha of nu n and mu. So this could be summarized into constant nu n minus mu. Grunwald's inequality, which serves us a lot in this work, says that up to a constant, we get this bound. But how can we bound this term? So for this, we're going to use Buchholder-Davis inequality. We want the expectation of this thing to be small. So for this, we're looking at the quadratic variation of a minus s, and the quadratic variation of a minus s of a tilde minus s tilde. Recall the 1 over square root of n, because it's quadratic variation. We have the 1 over n. It is being squared. And I don't care about this. The quadratic variation of a Poisson process or Cox process would just be the rate of it. Right? So the rate was n times lambda, n times sigma. So I'm dividing by n, I'm getting this. So this is finite. So when we have here, we have this 1 over square root of n, this would be bounded by order of 1 over n. Buchholder-Davis inequality will tell us, oh, you get the fluid limit or the law of large numbers that you really wanted. Okay. Okay. Now the interesting part would be the diffusion limit. The diffusion limit is the CLT. And here I'm using the same copy-pasted equation that we had from before. Now we're setting the square root n times this difference. So we rearrange everything, okay? When we multiply by square root of n, this is being killed. Okay, here at time 0, we said, oh, at time 0, this converges to something. And here we multiply by square root of n, this part. So if I just rearrange, what I get is that psi nt, this is psi nt, minus psi n0, this is psi nt. Psi n0 is this part. So now I have the blue minus red part here, plus some drift. I don't care about this. I'm just throwing all the junk there. But now I want to show convergence. So this is more, I guess, to the young folks that, you know, if you want to show convergence of processes, then we have a problem, because, or even functions, because if we want to attain some compactness, we need to make sure that the functions that are tamed. It means that they are, for example, if they are bounded with the same Lipschitz constant, we want to make sure that these functions are nice. The problem is much harder when we have processes. So on top of this, we have processes. So usually the way to deal with it would be through tightness of processes or probability measures. So the first condition says, oh, all these processes, they cannot go outside of some box, okay? Just box in the y-axis, just their height cannot be too high. And this condition, I'm not going to go over it, it just says that the oscillation of this function is not too big, okay? And there is a way to set it up with probability. So for this, we have, if we show C tightness, which means that this process, each of these processes that we have in this graph is tight. C means that the limit is continuous. So C tightness plus C tightness tells me, oh, you can take convergence of each one of them separately, and then you would get that the sum convergence, you would have this continuity. So here, to show the C tightness, we're taking the quadratic variation again of A minus S, one time with the state X, one time with the state Y. What we get is this. This is just, the calculation here is not complicated, but since I don't have much time, I would just skip this. It would just be, this is the empirical distribution up to an order of n of the players in state number y times the rate to move from y to x. Here it would be the rate to move from x to y. So I'm taking the sum of them. The martingale central limit theorem will tell me, oh, A tilde minus S tilde would converge to some diffusion process. So now I'm getting C tightness of this. C tightness here is easy because Bn is going to be bounded because of some assumptions in the model. We have the finite state. And then we have C tightness arguments plus the fluid limit. The fluid limit tells me, oh, this nu n converges to mu. So I can characterize stuff with the Bn, or here with this nu n that we have some characterization. And the boundedness, Lipschitz continuity, a lot of technical arguments would give me this trick. So now I want in the next 4 minutes just to say a few more words on conclusion and future outlook. So what I presented today was characterization of the limit of the value function, the optimal control, and the empirical distribution. We gave fluctuation results. We gave convergence rates. I did not mention how I solved the coupled forward-backward PDE in details. And I showed you some probabilistic tools how to deal with this work. And now some results, some of them already been established recently. So social planner. So suppose there is one person that is trying to take care of the benefit of the social welfare of the players, the average cost. So recently, Chechin has a paper about finite state and agent and mean field control problems. So we control the mean field, we control the behavior of the kids. One can have a model with social planner and common noise. So for example, in this model, suppose that you have these creatures and the right Fisher says, oh, there is a rate. Okay, there is a way to set up rates in this model such that they meet and then they duplicate each other. Think about blue eyes, green eyes, brown eyes. So when people get married, then the kids can be either here or there. There is also a model of common noise where there is another source of nature that gives noise to all the other players. So the first paper here by Bertucci, Lazary, and Lyons was done with more or less, I don't want to say this octopus, but there is a gigantic force that moves all the players. In a recent work with Francois Delarue and Chechin and Bayraktar, we show that there is a way to inject right Fisher common noise, that these are many, many small noises like what we had before. And this gives us uniqueness without the monotonicity condition. This is what I wanted to say, without the monotonicity condition. And then Delarue and Chechin used these results to show that you have uniqueness of the solution of the master. You have uniqueness of equilibrium when you inject this type of common noise, and they used it to select a equilibrium. We can also have graph structure. One can think about mechanism design, like you want to attain a certain equilibrium. How do you engineer the cost functions? And you can think about real-world applications. And that's it for my talk. So thank you very much for your attendance.